In this video, we'll look at the RL circuit. If we have a resistor and an inductor wired in series, and at some point we switch into that and a battery or some type of other EMF device that tries to drive a current through this circuit. If we remember, we looked at the dual of this circuit, which was an RC circuit. So we were charged and discharged our capacitor. When we were charging the capacitor, we were building up the charge. The charge couldn't build up suddenly on the plates of the capacitor. It built up according to our charging equation. Eventually, over time, enough time, then the charge on the plates of the capacitor was our Q is equal to CV. It was the capacitance of the capacitor times the EMF device that we were using to charge the capacitor. But relative to our time constant, it took 5 or more time constants for that capacitor to become more than 99% charged. So the capacitive time constant was RC, the resistance in the circuit, times the capacitance in the circuit. If you also recall, we've talked about in the last video how the dual of a capacitor is an inductor. We'll see how also that the dual of a resistor is 1 over the resistance, or a conductance. And that's how we can find our inductive time constant, or remember our inductive time constant. If we were trying to reduce the charge on the capacitor, then we flip the switch in this direction, and the charge that was on the plates of the capacitor moved via a current and recombined with the negative charge on the other plates of the capacitor. It couldn't do that instantaneously. It also did that with the time constant, and eventually, after 5 time constants, we had less than 99% of the charge left on the capacitor. So then the analogy or dual of this is the slowing of the rise or the fall of the current flowing through the inductor when we introduce an EMF to the device. So if we switch our switch such that we tie a battery in through the resistance and our inductor into a single loop circuit, we're going to increase the current that's going to flow through the device. But the current cannot change instantaneously in the inductor, just like the charge on the plates can't arrive instantaneously on the capacitor, or the voltage, which meant that the voltage couldn't change instantaneously across the capacitor. So we'll have similar charging and discharging equations, and we'll solve for a similar time constant. So if we take our circuit and we switch up to switch A, so we can suddenly apply an EMF to the device, initially we know that that solenoid is going to resist this a magnetic field changing inside its core, but we're going to look at the inductor. The inductor is going to resist the change in current through its coils. So it's going to create a current. Actually, the EMF wants to create a current in this direction. Our inductor then will create a current in the opposite direction by creating an EMF then in this direction. Eventually, though, that dIdt is going to go to 0. We'll end up with steady state. So at steady state, when we our voltage across our inductor, VL according to our passive sign convention, is our L dIdt. When dIdt goes to 0, so does the voltage across the inductor, and so it's going to look like a short circuit. Initially, it's going to resist current, and it will look like an open circuit. So we can solve for that using our loop equation. If we recall, our loop equation is we move from this point in the loop, we'll go clockwise around our loop in the direction of the EMF arrow. EMF, E minus IR, we subtract in the direction of current through the resistor. Now we're going in the opposite direction of the EMF for our inductor, so we have minus our L dIdt, or we can rewrite that as our dIdt plus R over Li is equal to E over L, our EMF divided by the inductance. Our solution to this, we'll show the solution on the next page, but our solution to this is that the current through the inductor is equal to the EMF divided by the resistance times 1 minus our negative R over LT, where R over L is 1 over our tau L. So our time constant for an inductive time constant is L over R. If we recall, our capacitive time constant was RC. The dual of that is 1 over R for the dual of R, L for the dual of C, so you get your L over R. So that's how a current is introduced through an inductor. As time goes to infinity, t is our variable here. As time gets very, very large, where our e to the negative something very, very large becomes 0, and so we end up with just our current being e over r, so our inductor looks like a short circuit. If time is 0, e to the 0 is 1, and our current is 0, and our inductor looks like an open circuit. Solving this differential equation, we can use separation of variables. We separate t and we separate I, and then if we do our integration without our we need our constant of integration. We'll leave just one constant of integration with t. If we integrate di divided by e minus ri, we have the natural log of e minus ri, but we have then we have to bring out our 1 over negative r. Then we use our initial conditions to solve for our constant of integration. Our initial conditions was that the current was 0, so we plug in at t is equal to 0, that I is equal to 0, and find a constant of integration. And we plug our constant of integration back up into this equation, and then we go and solve for that. So our natural log of e minus ri over e, that's the same e, it looks different, is equal to negative r over lt, and then we can solve for what we want to solve for is our current I, and we can use that to solve for our current I, and that's true at t greater than 0. It's actually true at t greater than or equal to 0. So to analyze that, when we're charging an inductor, our charging equation, we call it charging, but we're introducing a current through the inductor. If we look at initially, when t is equal to 0, when that switch is first flipped, then we plug in 0 for t, and we end up with that current is equal to a 1. E to the 0 is 1, so it's 1 minus 1. That's equal to 0. If we look at after one time constant, then we have e to the negative 1. So we have 1 minus approximately 0.37. So we end up, we're at 63% of just e over r, which is, after 10 time constants, is approximately the EMF divided by the resistance, where the inductor is no longer resisting the change in current at all, so it just looks like a wire, which is what it is. It's a wire that's coiled around, so it looks like it has a wire with no resistance. If there is some resistance in the inductor, we can model that as in terms of this resistor here. So the current that we introduce through the inductor increases, the current that we introduce to the inductor increases like this. What happens to the voltage across the inductor? The voltage jumps up initially to the EMF, and then it decreases. But let's look at, so when at time t is equal to 0, when we first flip that switch, our inductor looks like an open circuit. After a very long time, our inductor looks like a short circuit. If we look at the voltage across the resistor, well, that's just our current. That's how we can model our current, right? If this could be our current equation, or it could be a voltage across the resistor. Our voltage across the inductor, we can use our negative L di dt. But again, that's if our voltage across the inductor is in this direction, as though we have an EMF device. So that's going to be our L. We can take our derivative here, and we end up with, that's going to be our EMF times e to the negative t over tau L. So it jumps up to the size of the EMF so that our current is 0 through the resistor, and then it's slowly that voltage dies away, so we end up with a short circuit. Open circuit, short circuit. So let's look at this problem here. We have 3 different circuits. We have identical batteries, and we want to rank the circuits according to the current through the battery just after the switch is closed, and then a long time after the switch is closed, and we're going to rank them greatest first. So just after the switch is closed again, the inductor is an open circuit. A long time after the switch is closed, the inductor is a short circuit. So that simplifies the problem a little bit. So if we, just after the switch is closed, if it's an open circuit, if this is an open circuit, that's as though this isn't here at all, right? It looks like this. Well, what current can possibly flow through this circuit? And the current's not going to flow into a bucket. So in this case, I is equal to 0, T is equal to 0. So it's not going to allow, and that's the only way it can not allow current to flow. Basically what it does is it sets up across here, it sets up, we want to know the current. So the current's equal to 0, but our VL in this direction is going to be equal to whatever our VB is. VL is equal to VB. And so in this case, for 1, I is equal to 0. For 2, again, if this is an open circuit, then this current is going to be equal to 0. So the only thing that this battery is going to see is this resistor here. These resistors are both the same. Those are R and R. Then in this case, I is just going to be equal to the battery divided by R. In this case, if this is an open circuit, right, then this current is equal to 0. I is equal to 0. Now, we're going to have current flowing from the battery around here. So, in this case, our I is going to be equal to divided by R plus R, or 2R. So, this is I1, I2, I3. So, our I2 is greater than I3, which is greater than I1, which equals to 0. Let's look at the case where after a long time after the switch has been closed, then our inductor is going to look like a short circuit. So if our inductor looks like a short circuit, it's just going to look like a wire, right? It's just going to look like a wire here. So now, that's been closed for a very long time, right? So now we're at some, we'll say T is equal to infinity. So now our current I1 through the circuit, I1 is going to be equal to our V of our battery divided by, this is R, and this is R, divided by 2R. In this case, though, we have our current's going to flow this way, and then it's going to divide, right? So we're going to have a current flowing our battery, right? What we want to know is our I battery. It's going to flow here, but we're going to end up with IA and an IB, right? So the current's got to divide. So here we are V battery divided by R in parallel with R. Here the two R's are in series, resistors in series, R plus R, resistors in parallel, 1 over R plus 1 over R. So that's going to be equal to R over 2. So here our current is going to equal I2 is going to be equal to V battery divided by R over 2, or equal to 2 V battery divided by R. So instead of V battery divided by 2R. So this current is going to have to be 4 times I2 is equal to 4 times I1. So that's obviously greater. If we look at this circuit here, this is shorted, so this current's going to flow, and no current's going to flow down here because all the current's going to end up flowing this way because this is a short circuit. So our I3 is just going to be equal to V battery divided by R. So that's V battery divided by R. So we have I2 is greater than I3, which is greater than I1, right? So which is the least. And in fact, I2 is equal to 2 times I3. So we'll look at more examples in the next video.